And now we have the Thesis Award, the KD Abhyankar Best Thesis Presentation Award for this 42nd meeting at ASI is awarded jointly to Dr. Partha Pratim Goswami and Aruna Goswami with the title Chemical Abundances of Metal Poor Stars as Probes of Neutron Capture Nuclear Synthesis.
Hello. Thank you, sir. Am I audible? Yeah, okay. Good morning, everyone. I am Partha Pratim Goswami. I did my PhD from the Indian Institute of Astrophysics under the supervision of Professor Aruna Goswami. As you can see, I will be talking about chemical abundances of metal poor stars as probes of neutron capture nucleosynthesis. This is my thesis title. The main results of the thesis have been presented in these 8 papers. As the title suggests, my thesis is primarily aimed at understanding a very fundamental physics problem, that is neutron capture nucleosynthesis. And we attempted to understand neutron capture nucleosynthesis by studying the chemical composition of metal poor stars. So first, I'll briefly discuss what neutron capture nucleosynthesis is, and then I'll go to metal poor stars. We know that the elements up to iron are produced by fusion, and the elements which are heavier than iron, it is not working, which are heavier than iron cannot be produced by fusion. These elements are produced by neutron capture nucleosynthesis. Classically, there are 2 known neutron capture processes. One is S process or slow neutron capture process. The other one is R process or rapid neutron capture process. As the names imply, for S process, the neutron capture time scale is much longer than beta decay time scale. And for R process, the neutron capture time scale is much shorter than beta decay time scale. For R process, the required neutron density is around 10 to the power 15 times more than that of S process. And the proposed sites for both the processes are also different. For S process, the proposed sites are low and intermediate mass AGB stars. And for R process, the proposed sites are supernovae and neutron star mergers. It is not working. Oh. Okay, so we come to metal poor stars now. Here I have shown 2 sample spectra. The yellow one is the spectrum of the sun, and the red one is the spectrum of one of our program stars. And we can clearly see the difference between the number of lines and the strength of lines in both the spectra, because the metal content of our program star is 1,000 times less than that of the sun. So these are metal poor stars, and metal poor stars are population 2 stars, which are formed from the ejecta of the first stars in the universe. So they carry the imprints of the early universe, and by studying the chemical composition of metal poor stars, among many other things, we can trace back the origin of neutron capture elements and their production sites. Because a large fraction of metal poor stars, such as barium stars, CH stars, and carbon-enhanced metal poor stars, exhibit enhanced abundances of heavy elements in their atmosphere. By the term heavy elements, I mean the elements which are heavier than iron. For this work, we have selected our program stars from several metal poor star catalogs in the literature. We have acquired high-resolution spectra of the program stars using different telescopes across the globe. We have used the radiative transfer code MOOG to analyze our spectra. We have taken our atmospheric models from the Kourous grid of model atmospheres. We have derived the atmospheric parameters of the program stars. We derived the abundances of 24 to 30 elements of each program stars. So based on the elemental abundances, we have classified our program stars into several metal poor star categories. We have found 1 normal metal poor star, 5 barium stars, 1 CH star, 6 camp S stars, 3 camp RS stars, 3 extremely metal poor stars, and a star which is a very unique star that I am going to discuss in our upcoming slides. So the first highlight of the work is we have performed first time detailed high resolution spectroscopic analysis of 20 metal poor stars. A major portion of the thesis has been dedicated to the study of carbon enhanced metal poor stars or CAMP stars. This is a very interesting class of objects. Based on the enhancement of neutron capture elements, CAMP stars are classified into 4 subgroups. In CAMP no stars, heavy elements are not enhanced. In CAMP S stars, S process elements like barium is enhanced. In CAMP R stars, R process elements like europium is enhanced. And in CAMP RS stars, both S and R process elements are enhanced. So this subclass of CAMP stars draws special attention because I have already discussed that S and R process elements are produced in completely different stellar environments with different physical conditions. But these stars are carrying both S and R process elements. In our thesis, we have mainly focused on the study of CAMP S and CAMP RS stars. As the first project, we tried to understand the formation scenarios of CAMP S and CAMP RS stars in context to the program stars that we have. This is the formation scenario for CAMP S stars. Let us consider a binary system. Here one star is slightly massive than the other one. So the slightly massive star will evolve faster. It will evolve to AGB phase. AGB phase is the end phase of stellar evolution for low and intermediate mass stars. And in the AGB phase, a star can produce S process elements and carbon. And in the AGB phase, the star loses its envelope. And during that process, it gives S process elements to the companion. Now the companion star becomes an S process enriched star. And after the AGB phase is over, a white dwarf remains. This is the most widely accepted formation scenario for the formation of barium stars, CH stars, and CAMP S stars. Because all these stars are enhanced in S process elements, and all these stars are found in binary systems with an invisible companion, which is a white dwarf. Now we come to the formation of CAMP RS stars. I have already discussed that CAMP RS stars contain both S and R process elements. So there are several scenarios proposed for the formation of CAMP RS stars without any conclusive evidences. In this paper, we have discussed all those scenarios in context to our program stars, and we found that none of the scenarios can explain the abundance peculiarities of the CAMP RS stars that we have studied. Because in all these scenarios, it is considered that S and R process are produced in different stellar sites, and somehow they come to the star that we are observing as a CAMP RS star now. But there is a tight correlation between S process elements and R process elements. And this correlation is found for both CAMP S and CAMP RS stars. This correlation of S and R process elements cannot be explained if it is considered that S and R process elements are produced in different stellar sites. Therefore, an intermediate process or I process has recently been suggested, which can produce both S and R process elements in a single stellar site. Now this I process is intermediate in the sense that the required neutron density is intermediate to that of S process and R process. In S process, the required neutron density was 10 to the power 7 to 10 neutrons per centimeter cube. In R process, the required neutron density was 10 to the power 20 to 25 neutrons per centimeter cube. But for I process, the required neutron density is 10 to the power 12 to 15 neutrons per centimeter cube. And there are several proposed sites for I process as well. But the one which has got more confidence over the last few years is the low and intermediate mass AGB stars, similar to that of S process. Then we tried to see whether I process can explain the abundance peculiarities of our CAMP RS stars, whether I process models can reproduce the observed abundance patterns of our CAMP RS stars. And we used the I process yields from Hempel et al. 2016. And we extended the study to 8 more CAMP RS stars found in the literature for which the production channels were not studied. We found that I process models with neutron densities of around 10 to the power 12 to 15 neutrons per centimeter cube can reproduce the observed abundance patterns of our CAMP-R stars very well. So this is the second highlight of our thesis. We have confirmed the recent claims that I process is responsible for the formation of CAMP-R stars. Our project 2 is motivated by an outlier, HD 145777, which could not be classified into CAMP-S or CAMP-RS groups by any of the existing classification schemes. Some classification criteria put this object into CAMP-S group, some classification criteria put this object into CAMP-RS group. So this object compelled us to revisit the classification schemes of CAMP-S and CAMP-RS stars. We have critically examined all the existing classification schemes of CAMP-S and CAMP-RS stars. Here I have shown two of them. This is the first classification criteria given by Beers and Christlip 2005. This is based on barium by europium. And this is the recent classification criteria given by Hansen et al. 2019. This is based on strontium by barium. Now here the red grid is the region defined for CAMP-RS stars by the respective classification schemes, and the black grid is the region defined for CAMP-S stars. We can see that the stars are everywhere. So these classification schemes cannot distinguish CAMP-S and CAMP-RS stars. So we have put forward a new classification scheme based on the abundances of barium, lanthanum, and europium. Here the red grid is the region defined for CAMP-RS stars, and the stars which fall in this black grid region, we have to look for europium abundance for those stars to classify them as CAMP-S or CAMP-RS. And we found that this classification criteria can distinguish CAMP-S and CAMP-RS stars very well. So this is our third highlight of the thesis. We have put forward a new classification scheme based on barium, lanthanum, and europium to distinguish CAMP-S and CAMP-RS stars. Our third project is about a very peculiar star that we have discovered. This is HE1005-1439. This is a first of its kind object, and this is an extremely metal poor star with metallicity minus 3.03. We classified this object based on our classification scheme, and this is a CAMP-S star according to our classification scheme. But the ratio of heavy S-process elements to light S-process elements of the star is very close to that of CAMP-RS stars. So we tried to see whether S-process models or I-process models can explain the abundance patterns of the star. We found that neither S-process nor I-process can reproduce the observed abundance pattern of the star very well. But a combination of S and I process with similar contributions from both the processes can reproduce the observed abundance pattern of the star. So this star contains 56% S process contributions and 44% I process contribution. So this object forms a new class of objects with a distinct abundance pattern that has never been observed before. We proposed a formation scenario for this object involving a binary picture where in the AGB star, S and I process can operate one after the other, and it pollutes this star that we found as CAMP-IS star now. And this object is expected to reveal many unknown details about this AGB evolution. So this is our fourth highlight of the work. We have identified a new site where S and I process operate in succession. Our fourth project is about barium stars. Barium stars are slightly metal rich than CAMP-S stars. Barium stars are also S-process enhanced. So depending on the enhancement of S-process elements, barium stars are classified into mild barium stars and strong barium stars. Although it is known that both mild and strong barium stars are produced through the same AGB mass transfer scenario, but it is not known how they get such different levels of enhancement. We derived the mass distribution of the barium stars, and we found that mild and strong barium stars occupy the same mass range. Then we derived the mass distributions of the progenitor AGBs of the barium stars, and to the best of our knowledge, this is the first attempt to do so. And we found that progenitor mass distributions of mild and strong barium stars peak at different values. So we propose that the initial masses of the progenitor AGBs of barium stars dominantly control the formation of mild and strong barium stars. This is the last highlight of the thesis. We have derived the mass distributions of the progenitor AGBs of barium stars and found different mass distributions for the progenitors of mild and strong barium stars. I have already highlighted the main achievements of the thesis. Let me end my talk with a take-home message for those people who are not from this particular field. This is a picture that I painted for my thesis. This was an idea till 2014. It was considered till 2014 that heavy elements, the neutron capture elements, are produced through S and R processes. But our current understanding of the galactic chemical evolution says that I process also contributes to the galactic chemical evolution. Thank you.